4 is going to be using that change of base theorem. So we're going to be looking at question 3. And we're looking at earthquakes. Earthquakes are on, again, the logarithm scale, which is the Richter scale. Okay, Richter scale is a version of the logarithm scale. An earthquake was recorded with an intensity of 125,893 times more powerful than the reference earthquake level. What is the magnitude of this earthquake on the Richter scale? And the Richter scale is log base 10 of I over I naught. So what does our formula look like? There's no 10 in front of there, right? It just says, that's our, actually I didn't cut off the 10 there. I don't think it was 10. I thought it was the decimal scale where they had a 10. Let me look something up real quick. We're just going to use our logarithm scale. I want to make sure that that's the right formula. And that's in 4. I was thinking there was a 10 in front. Maybe not. Nope, there's not. Okay, so I want to make sure there wasn't 10 in front. I couldn't remember. Okay, but here's our formula. We've got log. Now, I'm not going to put the 10 down below because we understand that it's just a log base 10. If there's no number, we understand it's 10. So I'm not going to put that on there, but it's I over I naught. Now, when we talk about these earthquakes and decibels, we have to reference it to the natural shaking of the earth. And it's how powerful that earthquake measures compared to the initial shaking of the earth that happens all the time just due to the earth itself. So what we're looking at here is we've got our I, which is going to represent that earthquake, and it's 125,893 I naught over I naught, because that's our initial condition. Now, what's going to happen with the I naughts here? One's in the numerator, one's in the denominator, so they are what? They are gone. And now all we need to do then is use our calculator to take the logarithm of this number. So we're going to take the logarithm of 125,893. So we just use our calculator here. It's log base 10, so we don't have to convert anything. We can just directly use our calculator. And we want to round, let's see, it didn't say how far to round. It's just going to come out, it says round to the nearest tenth, and it looks like it's going to be a 5.1. So that earthquake would measure then 5.1 on the Richter scale. Is everyone all right with that? So we just plug our values in, and we just use our logarithm. We don't have to put log 10 here because we understand that it's already log base 10. If it was a 3, we'd have to deal with it separately. We'd have to use the change of base. But if it's a log base 10, we don't even have to put the 10 there. Question 7. This one's working with population growth. So we've got a formula, and we're going to be plugging a value in. So the population growth of an animal species is described by this formula, where T is measured in months. Find the population of this species in an area 6 months after it's introduced. So we have a population model for a new species, and that's going to be f of t equals 400 log of 2t plus 3, and we want 6 months, so that means my t is going to be 6. So that is then 400 log of 2 times 6 plus 3, which is then simply log of 15. And 400 out in front. And what does that then come out to give you? We just need to find our 15, log of 15. Multiply that by my 400, and that's going to give you, didn't say how far to round. We'll just take this out to 1 decimal place, so that's 470.4. That's going to be your population. Or you could just write 470, that's fine. Again, this is a model, so you may have a little more, a little less, but it gives you an idea of if I introduce this new species, probably had initial population of 400, in 6 months it should be at about 470. Okay. Logarithms and exponentials are used for population modeling. If you take a statistics course, you take elementary statistics, you're going to be using a lot of exponentials and logarithms. The decibel scale is just like the earthquake scale, only it has a 10 in front. So that's our decibel scale. The only difference between the decibel scale and the earthquake scale, the Richter scale, is the fact that on sound we have a 10 in front of our logarithm. Okay, so we want to find the intensity of this sound if I naught is 10 to the negative 12th power, and we want to know what that sound intensity is at 93 decibels. So we're going to fill in our pieces. So our decimal, or decibel, is going to be 93 decibels, and that's 10 log of, okay, I we don't know, but we know I naught is 10 to the negative 12th power. Okay, and I think we may have done this one in class last time. But we'll go over it again, just so we remember how to do this. Because when we look at 4-5, we're going to have to be using this technique to solve some of the logarithm equations. So what are we going to do? Well, we want to get rid of the 10, right? So we want to get that logarithm by itself. So we're going to divide both sides by a 10. And when I divide both sides by that 10, then that comes out to be 9.3 equals now log of I over 10 to the negative 12th power. Now, what do we need to do? Well, we need to remember how to get rid of a logarithm. And whatever logarithm base we're looking at, we use a power to get rid of it. So this is log base 10. So in order to get rid of a log base 10, we use a 10 power. And so that's that power of 10, that gets rid of a log base 10. If it had been log base 2, we would use the second power. If it would have been an ln, we would use an e. So we're going to work this out, and that's going to give you 10 to the 9.3 power equals that logarithm and that 10, they're inverses, they cancel out, and that's I over 10 to the negative 12th power. What can we now do? Well, we can cross multiply. And then we'll use the fact that we can add these exponents together. So what do we know about these? With our rule for exponents, these bases are the same, right? And if the bases are the same, then we can combine the exponents. So remember, in exponents, if the bases are the same, multiplication of these becomes addition. So that becomes 10 to the 9.3 minus 12 equals our I. And 9.3 minus 12 comes out to be a minus 2.7. And then, bless you, how do we finish this out? We take 10, we hit our YX key, 2.7, we make it negative, and then that gives me then I equals 0.001, well, if we round 200, close enough. And you don't have to be exact on the rounding, right? If you're off a little bit, that's okay, as long as it's close. The main thing with logarithms is they're used for prediction, and they can be off a bit because of our calculators, and it's not an exact sign. So if you're off a little bit in the rounding, that's okay. Not a big problem. I would have taken 0.00200. I would have taken, if you wrote this down, if you would have wrote 0.0019, I would take that. I'm not that really picky about the rounding as long as you're close. So that takes care of that one. Now, in 4-5, we only did 1 through 5. These require a little bit of thinking as to how to solve them. They're all a little bit different. But we are going to learn how to solve question number 2. And some of these may require different tricks. They may require to use rules for exponents. They may require a substitution, which we'll learn about those today. Just different tricks. You may have to try to get the bases the same. You may have to convert them to an exponential. A variety of different techniques are going to be required to solve some of these. So question 2 is log of x plus 3 equals 1 minus log of x. Okay, now how are we going to solve this out? Well, what we want to do, and here's going to be our ultimate goal. When I see this, I want to try to get all the logarithms together in one log. Okay, because once we get them together, then I can use a power of 10 to get rid of the logarithm and solve the resulting equation. So the first thing I'm going to do is I'm going to go ahead and add that log base x over. That way they're together on the left-hand side. So is everyone all right with that so far? Now, once we've gotten to this point, then we need to think about what we can do. And we have lots of different properties of logarithms. Our goal is going to be get these logarithms together into one log. And we have this property here. Okay, we have this property that says if we have 2 logs and they're added together, that can become one log as multiplication. Right? So addition can become multiplication. So you can split it up either way that needs to be done. So what I have now is I've got addition. So I can rewrite this as one logarithm with multiplication. Is everyone all right with that? So I combine those logarithms into one log. Now, why did I do that? Our goal is to get rid of the logarithms. So we want all the logarithms together combined into one single log on the left-hand side. Now, how do I get rid of a logarithm that's base 10? Just like we did on the last one. We need to get rid of that log base 10, so I'm going to take both sides to the 10th power, or 10th base. So that's going to get rid of this logarithm, and that's going to get rid of that 10. Now, what about on the right-hand side? So the left-hand side is simply going to come out as x times x plus 3. There's nothing to worry about there. What about 10 to the first power? Well, any number to the first power is itself. So 10 to the first power is simply 10. Now we have something that we can deal with. So now we have used our properties, we've manipulated it around, we've gotten rid of all the logarithms, and now we can distribute through, we can set this to 0, we can factor it, and we can finish it. And again, they're all a little bit different. They require a lot of different techniques. That's why I wanted to start this section last time on Tuesday, so we'd have plenty of time to look at different examples. And this is by far and away one of the more difficult sections. On your final, you're not going to have anything that's this complicated though. It's just in the homework. Do I give you challenging questions? So distribute that x squared through, or that x through, and we get x squared. plus 3x equals 10. Now what do? We move our 10 over, and now we've got something that we can solve. Right? We should know how to factor this. And this should factor out nicely, because first times the last is going to be a negative 10. And what two numbers multiply together to give you 10, subtract from each other to give you 3. Okay? And middle sign is positive, so we need a positive 5 and a negative 2. We can jump to our factors, so we have x plus 5, x minus 2 equals 0. So that gives me x equals minus 5, and x equals now 2. Is everyone all right with that so far? Now, one of these may or may not work. We have to check and make sure that when we plug it into the logarithm, you're not taking the a logarithm of a negative number, because you cannot do that. Negative numbers inside the logarithm do not exist. Now, if we go back up and we look here, okay, let's look at our original. It's x plus 3 here. Well, if I try to plug in a negative 5, right, one of our possible solutions is negative 5. Minus 5 plus 3, that makes it a what? Minus 2. Can we take a log of negative 2? No. So therefore, we got two solutions, but that one won't work. And why won't it work? It won't work because it would give you a negative logarithm. Okay, if you use that one, that would give you negative inside the logarithm. And we can't have that. So the only solution for question 2 would be what? 2. Right? You get two possible solutions, but again, you have to go back and make sure that they actually work in the logarithm itself. Did we have any others out of 4 or 5 to look at? Do we need to look at any of the others from 1 through 5? Anything else? Okay, well, if not, then we're going to start working with some different ones. And lots of different techniques we're going to be going over. So from 1 through 5, we learned 2 basic techniques. How to get rid of a logarithm. Okay, that was 1 through 3. And how to work with exponentials. Now we're going to have to learn about how to use some substitutions. And this is going to work with question number 6. So we're going to do one very, very similar to question 6. What's going to happen is we're going to use a substitution. And then we're going to take that, solve it, and then substitute it back. So let me find one here that's similar to question 6. So I'll pull these from our homework. Question 36. This is on page 497. We're going to look at question 36. Okay. And this is going to be very, very similar to question number 6 in the homework. So what we have is we have this. We have e to the 2x power minus 8 e to the x power plus 15 equals 0. Now, what we are going to do is we are going to try to factor this. And you can either factor it as it is, or you can use a substitution. I think the substitutions are going to be a little bit easier to work with. Now, what I can do is I can rewrite this and I can change things around a bit. So I'm going to rewrite this as this. I'm going to rewrite this as e to the x quantity squared, and we'll see why. We can rewrite that with our rules of exponents, minus 8 e to the x plus 15 equals 0. Now, We can either use a substitution or we can just directly factor it. I'm probably going to use a substitution because I think it might be a little bit easier to visually see. For this substitution, I'm going to let u equal e to the x. And this is a very, very important technique that you are going to use a lot if you take calculus. If you take calculus 1, we use substitutions constantly. It's basically a game of substitutions. Now, what's going to happen when I do that? So I rewrote this e to the 2x. I can split it up into this, e to the x quantity squared. If I plug in the u, well, that's going to be u squared minus 8u, right, because e to the x is u, plus 15. Now you can visually see what we've got, right? Once I plug the u in, what does it now look like? Well, it looks like a polynomial that we can factor, doesn't it? Right? Instead of having x's, though, we have u's. So we broke up that e to the x from that e to the 2x into e to the x quantity squared. We let u equal e to the x, and you're going to use the same technique on question 6 in your homework. Almost identical. Now, how do we factor this? This is factorable. First times the last is a 15. And negative in the middle. 15 is a positive, so they're both negative. What two numbers multiply together to give you 15, add together to give you 8? Both negatives. 5 and 3, right? So we need a negative 5 and a negative 3. That is then u minus 5, u minus 3 equals 0. And now what can we do? Now we can solve it for u and then resubstitute it back. So u minus 5 equals 0. Well, that gives you u equals 5, but what is u? E to the x, right? We substitute it back. Now, we did talk about this a little bit last time. How do we get rid of an exponential? How do we get rid of that e? The opposite of an e is going to be a ln. Remember, e and ln are inverses in your calculator. If you have a calculator, you can even see that. Remember, look at your inverses. You look at your ln. See your ln key? What's the inverse of ln? E to the x. See how they're inverses? So how do we get rid of an e? We use an ln. And that is then going to cancel out with the e here. And we've got x equals the natural log of 5. And what is that going to be when we round? We'll round out to 3 places. The natural log of 5 would then be, using our calculator, ln 5. That's going to be then 1.609 if we round close enough. So there's that one. Now, what about the other one? U minus 3 equals 0. So u equals then 3. What is u? E to the x. How do we get rid of an e? We use an ln, right? They're inverses of each other. And that gives me then x equaling the natural log of 3. And using our calculator, the natural log of 3 is then 1.097 if we round. Not 97. 99. Close enough. So again, they all require different techniques. And I'm going to try to work an example out of each different type so you'll see how it's done. Sure. Well, you can see it this way? Okay. So let's talk about what we did. So I first took that e to the 2x and I wrote that as e to the x quantity squared. And the reason why I did that is I want to turn this into a polynomial that we can then factor. So then I had to use a substitution. So I let u equal e to the x. So you're going to use the same substitution for question 6 in your homework. So I did that, and then I factored it down, right? Because then you can see it. It's easy to factor. And then I got to that point. I then resubstituted back what u was, which is e to the x. And then how do I get rid of an e? I use the natural logarithm. And then we just evaluate it down in our calculator. And we only have to get it to 3 places. 3 places is usually enough. You can do more if you want, but try to keep it at least 3. So let's try some more of these. And again, they're all a little bit different, and they all require different techniques. So let me find another one. It's going to look like question 7. Okay, so let me find another one for us to look at. And again, they're all a little bit different. They require different techniques, different ways of thinking outside of the box. Let's look at an exponential here. How about we look at, let's see what we could do with this one. How about we look at this? Okay, let's try another one, a little bit different. How about we try to figure out how to work with question number, let's say 30, question 30. It's kind of similar to 7 and 8, a little bit different though, but we're going to look at question 30. And again, different techniques are required depending upon what we have. So we have 5 times 1.2 to the 3x minus 2 power. And then we've got plus 1 equals 7. Okay, so what can we do? Well, what we need to do is we need to first figure out how we can approach it. So what I would do is I would go ahead on this one, I would move that 1 over. So we'll move that 1 over. And that gives you 5 to the 1.2 power to the 3x minus 2. And that equals now, when you work it out, that equals now 6. Okay. Now what can we do? Well, different ways of approaching it. I'm going to go ahead, I think, and divide it by 5, and then we'll see where to go from there. And it's just a matter of thinking a little bit outside of the box and looking at this as a whole. And when I did that, now what do I know about 6 over 5? Well, let's see what 6 over 5 would be in the calculator. What's 6 over 5 in the calculator? Okay, 6 over 5 in the calculator is 1.2, isn't it? Now, why is that going to be important? Because this one is what? 1.2 for its base. Right? So if I divide that down, that's going to give you 1.2 to the first power equals 1.2 to the 3x minus 2 power. Is everyone okay with what I did there? Now, we normally don't write the 1 there, but it's always there. And we need that 1 because we're going to be solving this down. And what do we know? We've kind of looked at these before, back in 4.2, when we talked about exponentials. If the bases are the same, then what else must be the same? Then the exponents must be the same. So these bases are the same. And if these bases right here are the same, then this must equal that. So now we have 3x minus 2 equals 1. And that's something that we can quickly and easily solve. So we'll just add our 2. So 3x equals 3. So then that gives me x equals now 1. 1. Easy enough. And they all are a little bit different, but it's just a matter of working with these different bases and trying to find out what might work in each particular situation. Okay, let's try another one here. A little bit different again. We try to find one that kind of looks like what we're working with. Let's find, let's try, how about question 24? Let's see what we can do with question 24. And again, I'm just picking different ones that I think help you solve the homework. So let's look at question 24. A little bit different on 24. And again, they're all a little bit different. And 24 is going to require us to use the properties of exponentials. To finish this up, we've got e, 5x here, and that equals 2e. All right, so what can we do here? Well, there's different ways of working through it. Where I would begin is I would go ahead and combine these together. Everything has a base e, so if I was going to work with this, I would go ahead and put those together. Now remember our properties of logarithms and exponentials. Addition can become multiplication in exponentials and logarithms. Remember your property. A to the n, a to the m is a to the n plus m power, right? So when we multiply, if the bases are the same, the exponents can do what? The exponents can add together. So let's go ahead and do that. And this is then going to be e to the 1 minus 3x power plus 5x equals 2e. So is everyone okay with that? So a little bit trickier to work through and actually solve. Our goal, though, is going to be to get rid of that e using a logarithm. So that's going to be my ultimate goal here. So what's next? Well, we can combine. We can get e. We can put those together, and that's going to be 1 plus 2x equals 2e. Okay, and what else can we do? We've got some different properties that we can work with. We can take the natural log of both sides. Because a natural log and an e clear each other out. So let's try that. So again, all of them are a little bit different. But let's try taking the natural log of both sides. And what's going to happen here? Well, when I do that, that e and that natural log, those can cancel. Right? So that's going to go away, and that's going to give you 1 plus 2x on the left-hand side equals the natural log of 2e. And how can I work this one out? We've got different ways of approaching it. I would probably say just the easiest way would be to split it up. Because remember, we have this property, natural log or log base 10. They all have the same property. Natural log of xy equals natural log of x plus natural log of y. Right? We can split it up like that. So I can go ahead and split this side up into the natural log of 2 plus the natural log of e. And why did I do that? Well, the natural log of e, these actually have the same base, and that is 1. So That gives me 1 plus 2x equals the natural log of 2 plus 1. Because natural log of e is always going to be 1. Just like log base 10 of 10 is 1. Log base 3 of 3 is 1. Okay, if the bases are the same, and this is log base e, natural log and e, they cancel. That leaves you with a 1. Now we can finish it. So now I can move that 1 over. And that gives you now 2x equals the natural log of 2. Okay. And let's go ahead and break this down because now we're at a point that we can use our calculator. So we can use the natural log of 2. And that is 0.6931 if we round close enough. And that equals 2x. So we'll divide that then by 2. And we get our answer, which is then 0.347 or 65 either way. Well, we'll just do 66, close enough. And again, as long as you're close, that's okay on these. Rounding is not that big of an issue. Just make sure you get pretty close because you're going to have round off anyways. That one was a little bit trickier. We had to think about how to work it out using different techniques. Okay. Let's try another one. A little bit different on the next one. Let's think about how we would handle this one. Let's look at question 82. So question 82. This one has a square root. So question 82 is the log of x equals the square root of the log of x. Okay, so how would I handle this one? Well, we have a square root. Okay, and how do we get rid of a square root? What do we have to do to get rid of a square root? How do we handle that? We get rid of a square root by what? By square it. So we're going to square both sides. That's going to get rid of our square root. That then leaves you with log of x quantity squared equals log of x, right? Okay, how can we handle it from here? Well, we need to figure out some way to get these to go together. So let's go ahead. We could use a substitution. Let me just make sure I wrote it down right. Make sure everything is right here. Make sure everything looks the way it should. Okay, yep. It looks right there. Okay, so let's make sure we can work this one out. So we squared both sides to get rid of that. Now, we can use a substitution. Right, set a 0 and factor it. Or we can combine them together. Make sure that that square root's on the outside. Okay, so let's see what we can do. And again, they all require different techniques. So let's go ahead and set this to 0. So I've got this. Now, substitution. Okay, these are both log of x. Different technique. And there are some other ones we could do. We could combine them together, use powers of 10. Different techniques. I'm going to use substitution because they both have log of x. So I'm going to let u equal log of x. And that then gives you u squared minus u equals 0, right? So I'm going to use substitution. You could have used properties of logs, combined them together as division, and solved it that way. I'm going to use substitution. Now this will factor, because then I can take the u out, and that's going to leave you with a u minus 1 equals 0. And that gives you u equals 0. And the other one is u minus 1 equals 0, so u is then 1. Okay, now what can we do from here? Well, are we solving for u? No. What do we want? We want this. What is u? U is log of x. So let's plug that back in. So we know u equals log of x. So that tells you then the log of x equals 0. And what's the only number when you take the log of it that gives you 0? It's going to be 1. How else could I explain this? If I rewrote that as log of x equals 0, how do you get rid of a log? What's the opposite of a log base 10? Base 10. And what happens here? 10 logs cancel out. That gives you an x. And what about any number to the 0 power? Remember that property? I know you've seen it before. Any number to the 0 power is always what? 1. So that would give you one of these solutions, which is x equals now what? 1. What about the other solution? Okay. How do we get u equals 1? Well, if u equals 1, then that means log of x equals 1. And how do we get rid of a log? Base 10? We use a 10. So those cancel. And that gives you x equals now 10 to the first power, which is 10. So that's how you get the two solutions, which are 1 and 10. And all these require different techniques. Some are much easier to solve out than others. But they may require getting the same base. They may require using an exponential or a logarithm. Different techniques. This is kind of what calculus problems look like. A lot of times in a calculus course, if you go on and take calculus 1, you're going to have to use substitutions like this. It's all about substitutions. So you'd have to come up with a substitution, work it out, and then resubstitute it back. That's what you'll see more or less in a calculus course. Different problems, but a lot of substitutions. Let's look at another one that we can work with. How about we look at question number 54. Okay, let's see how we'd work out 54. Completely different type of question. And this one has a different base on it. This one's a log of 4. And I picked this one so we'd see how to use a different base. All right, well, what do we normally do to get rid of a logarithm? Okay, if it's a log, we use 10. Why? Because we know that if it's just log, it's log base 10. Natural log is log base e, so we use an e to get rid of it. Well, what base does this one have? This one has a base of 4, doesn't it? So how are we going to get rid of a log base 4? We use a power of 4. When I do that, then the log base 4 and the 4, those cancel. And that leaves you with a 3x plus 8 times x minus 6. And we now need to find 4 to the third power. And 4 to the third power is not 12. 4 to the third power is 64. So we have to use that because 4 cubed is your 64 then. Now we should know what to do. Right? So now we should know how to proceed from here. What are we going to do to proceed from here? Does anyone have any idea what we would do? Logarithms are all gone. What would we do? We would have to set it to what? What do we normally set things to? Okay, ignore this. If I gave you that, we have done these. We started with these back in chapter 1. If I gave you this to solve, what would I do first? Where would I begin? Don't even worry about the logarithms, just look at what I've got there. It eventually has to be set equal to what? What do we normally set things equal to? 0. Okay, now, before I can set this to 0, how would I handle this? This has to be FOILed out, right? So we have to FOIL it out and set it back to 0 and then factor it. You may see something like this on your final example. All you have to do is FOIL it out, set it to 0, and factor. This is something you may see on there. You probably won't see anything like this, but you'll see something like this. Okay, so if you just had this, we should know how to solve this, or where to begin. You begin by FOILing, right? Remember that? We did this way back in chapter 1. This is nothing new. We would FOIL this out. Okay, and so 3x times x, that's a 3x squared. 3 times a negative 6x, well, that's a negative 18x. We've got 8 times x, that's a positive 8x there. And we've got 8 times a negative 6. Well, 8 times a negative 6, would that make it a negative 48, wouldn't it? Okay. And that still equals now a what? 64. Okay, so we FOILed it out. Now we should know what to do. Now we have to combine it all together and set it equal to what? 0, so we can refactor it. I picked this one because this one's going to make us factor by grouping, I believe. I think we'll end up having to set it 0, factor it by grouping. So move that 64 over, and then those can go together. So now we have 3x squared minus 18 plus 8. That makes it a minus 10x. And we've got 48 and 64. They're both negative. Add those together. And we get a minus 112. And that equals now what? 0. Is everyone all right with what I did there? So I used a 4, power of 4, to get rid of that log base 4. Whatever you do to one side, you have to do to the other. Right? So this one and this one are the same, so take both of them to the 4th power. Those can cancel, and that gives you that 4 cubed there. 4 cubed is then 64, right? And then that gave us this. We could then go ahead and FOIL it out, combine like terms, set it to 0, and we should now be able to factor. This one is going to force us to do factor by grouping, because it's not going to factor out very nicely. I don't think we'll have to use the quadratic. No, it should factor, but it may require factor by grouping. So good review for us, factor by grouping. How do we factor by grouping? First times the last. First times the last is 3 times 112, and that gives you a minus 336. Okay, so let's review now factoring, because I think some of us may have forgotten about the factoring. What do we know about the signs of the two numbers? Are they the same or are they different? Tell me that. What do we know about that 336? It is a what? Negative, right? So if it's negative in that box, what do we know about the signs? Are they the same or are they different? They are different, okay? What's the sign in the middle? Negative. Right? Remember, it's been a while since we've had to do this. And that's why I picked this problem, to review again factor by grouping, because you may have a couple of questions on your final that involve maybe the quadratic formula, factoring, and factoring by grouping. Okay, so we know that the sign in the middle is negative, so that means we need a negative here and a positive here. Okay, so one's positive, one's negative. The sign in the middle dictates the larger number. Where do we begin? Well, 336, that's an even number. So let's start with a 12. I don't know that it'll work, but we're going to start with a 12. Okay, 12 and 28. 12 minus 28, what is that? 16. Fairly close. Okay, so we used a 12. Let's move up to a 14. Okay, 14 and 24. That works, doesn't it? Because we need a minus 24 and a positive 14. That is going to go together when we multiply to give us a 336. When they subtract from each other, what do we get? Negative 10, like in the middle. Okay? Now, we cannot just jump to our factors on this one. It's a little bit more complicated than that. What do we need to do? Because we have this 3 in front. Remember, we can't just go straight to our factors. We have to take that negative 10 and split it up. So now we've got 3x squared. We've got a minus 24x. We've got a 14x. And we've got a minus 112. What can we now factor out of the first two pieces here? What can come out of the first two pieces? Can someone tell me? What does 24 and 3 have in common? What number? These are both divisible by what? I know we know how to do this. Okay. 3 and 24, what do they have in common? What number? 3. Okay. And what else can we take out? An x. Remember doing this? It's been a long time, I know. We did this at the very beginning of the semester. Take out a 3x, and that leaves you then with an x minus 7. Right? What about the next two? Well, it has a 14. Let's see if that 112, if it has a 14 in it, because that's probably what we're going to need. If I use that 14, 112 divided by 14, that's an 8. Sorry about that. It should be an 8, not a 7. Why did I put the 7? My mistake. It's 24 divided by 3 is 8, not 7. I was thinking of 21. But 112 divided by 14 is an 8. Right? So I could take out a 14, and that's going to leave you with an x minus 8. Okay? And what do we know? Are the groupings the same? Yes, they are. So they are the same. So now we have an x minus 8. And we have a 3x plus 14 left over. And again, that is already equaling 0. Remember how to do these? I know it's been a long time since we did factor by grouping, but it's still a skill you have to have. X minus 8 equals 0. So one solution is x equals 8. What about the other one? 3x plus 14 equals 0. So 3x equals a negative 14. Divide by your 3. And x equals now minus 14 over what? 3. Those are your two solutions. And I picked that one because I knew it was going to force us to do factor by grouping. And we need a good review of factor by grouping. We've got a few more minutes. Let's do one more of these. Different type of question. They're all a little bit different. Well, actually, I'll work out an application. Just so we have one of these. So let me look at an application for us to look at. And these are just plugging in values. Okay, so let me find where we just plug a value in. Let's see. I'll just do one from the homework. I'll just do question 9 from the homework. You can do 10. I'll do question 9. You've got 2 of them from your homework. I'm going to do question 9. Now, these are just simply plugging values in. Suppose the government wants to impose a tax on fossil fuels to reduce the carbon emissions. The cost benefit is modeled by this. The natural log of 1 minus p equals a minus 0.0039 minus 0.0048x where X represents the dollars of tax per ton of carbon. And P represents the percent reduction in emissions of the carbon. Determine P when X is 52. And we're going to round this to 3 decimal places. So all we have to do is we are going to plug in X equals 52, and we're going to try to determine how we would solve this equation out. So that's all we have to do is plug the value in. So we're going to take our equation, and we're going to plug the value 52 in. Now 10 is the same way. You just plug the value in. So we need to eventually find P. And the natural log of 1 minus P equals a minus 0.0039 minus 0.0048x. And we're going to replace that x, in this case, with 52. So the x is going to get replaced now with a 52. So that's what we've got. We can work this out. Eventually what we want is we want the right-hand side to be a number. So we can take an e to get rid of that ln and then move it around and solve it for p. So that's my goal, is to get rid of this ln somehow. But before we can do that, the right-hand side has to be all combined together, which we can do. Right? We can do this pretty quickly. So let's go ahead and put this together on the right-hand side here. So we've got a minus 0.0039. We're going to subtract that from 0.00, oops, too many negatives there, 0.0048 times that 52. That's going to come out to give us now that, minus 0.2535. So I just put it all together, and that gave me that. That is on the right-hand side. Okay, so I combine it all together. Now, what do we need to now do? We need to eventually get to that p. But what's that p inside of? Natural log, ln. Okay, so how do we get rid of an ln? What gets rid of an ln? An e. So we're going to go ahead now and take both sides to the e power. Okay. Instead of the logarithm, we use an e. That and that cancel. So that gives me now 1 minus p equals, this we're going to use our calculator for. Right? This is just nothing but a calculator number. So here's the value. And we're just going to take the inverse ln of that. That gives us our exponential. Inverse ln. Okay, and that then comes out to be 0.776 if we round 1. You almost have it. Move that 1 over. So minus p equals now, subtract 1 from that. It's going to be a minus 0.2239. We'll divide that by a negative 1, and now we've got our value of p. So what is the value of p? P is going to be a 0.2239. And how far do they want you to round? Round it to 3 decimal places. So rounding it to 3 decimal places, that's going to be 0.22 if we round 4. That is what our answer is. And P represents the reduction percent in emissions. So P is in decimal form, but if you impose that tax, you should basically end